All right, hello. So in this video, we're going to look at implicit differentiation. Maybe. There we go. Okay, so far, we don't usually say this, but we've only been considering situations where you have explicitly defined functions. And we don't even really say explicitly. It's just functions. So y is a function of x or something like that. So example things like y equals x squared plus x, y equals whatever it might be. In both cases, y is explicitly defined as a function of x. That's how we usually think about things. So, but what we're looking at here is when we've got a situation where we've got a relation between, let's say, two variables, x and y. So you got an equation that describes some sort of relation between them, and you can think of one as implicitly defined in terms of the other, so an implicitly defined function of the other. There's plenty of reasons for being interested in this, and we'll get to that, but for example, kind of a classic example would be x squared plus y squared equals 4. You've got, and we'll see that in just a second, but my best attempt with my shaky hands here. You've got a circle of radius 2 centered at the origin, and you know, we might want to know things like rates of change and whatnot, and we'll get to that in a second, but that's what we'll be looking at here. So y is not an explicitly defined function of x because it's not y equals something, and in your pre-calc days or whenever you first start talking about this, you wouldn't even say it's a function of x because it fails the vertical line test, would have been the reasoning you gave back then. But we can think of it as implicitly defined as a function of x, or likewise you could switch roles and say x is an implicitly defined function of y. And so like we just showed in the last slide, this graph is something we're familiar with. It's a circle radius 2 centered at the origin. So it doesn't look like y equals f of x, but it's described by a relation between those two variables, y and x, and something like how is y changing with respect to x at a point is perfectly reasonable. So if I jump back, I might say, well, what's happening right here? How am I changing as I move x a little bit? How is y changing? So something like that, like I said, perfectly reasonable. So what we're trying to find then is dy dx, rate of change of y with respect to x. And when we have something where it's not explicitly defined, we can use an alternate technique called implicit differentiation, which is really just an application of the chain rule. So here's how it works. Implicit differentiation, if we've got y as an implicitly defined function of x, so described by a relation between the two. If we want to find dy dx, we're going to differentiate both sides using all the rules we know, power rule, quotient rule, whatever it might be. We're going to differentiate both sides with respect to x, and we're going to use the chain rule when we differentiate terms involving y. And then we'll solve for dy dx. We're going to have a bunch of expressions with some dy dx factors sprinkled in there, and it's going to be effectively it's a linear equation, and you solve for it. So here's an example, and everything's worked out, so you don't have to watch me write everything out. But back with our example that we had, x squared plus y squared equals 4. So that's circle centered at the origin with radius 2. So we've got our equation. What we said in the previous slide, we're going to differentiate both sides with respect to x. So differentiate this term with respect to x, I get 2x, just a basic power rule. Here I've got a function, I'm thinking of y as an implicit defined function of x. So I'm thinking of y as just a function. Imagine with the chain rule you had that function sitting inside the square term. So the outer function is a square, you bring that down 2y to the 1 times the derivative of the inside, which is dy dx. And then on this side we've got a constant, or if you like a constant function, and that derivative is just 0. So now, at this point, we solve for dy dx. And that's what we're doing from then on. So we start off with just the relation. Here we differentiate, and then we solve. So it's linear in terms of the y prime or the dy dx, if you like. So you take all the terms that don't have the dy dx, slide them over, as we know we can do, and then and then factor and divide appropriately, and you get dy dx equals something. Right, so if we wanted to know, if I had something like that circle there, and I wanted to know maybe something like what's the rate of change of y with respect to that point? Well, I'd have an x coordinate and a y coordinate, and it would be x divided by y. The negative of that would be the slope of that tangent line. And if you look, we're in the second quadrant where x values are negative and y values are positive. So x over y would be negative, and with that negative term in front, it would be positive. So we'd have a positive slope there. So that kind of makes sense. Hopefully we buy that. As we get closer and closer to x being 0, I get closer and closer to a horizontal line, which should have slope 0. That's reflected there. As I get closer and closer to y equals 0, get closer and closer to something out here or out here, get closer to a vertical line which should have undefined slope, which is reflected in that result. So this gives us a method for finding how one variable is changing with respect to the other. And usually we're going to have both variables involved in that description. Okay, so this is just a kind of a typed out summary of what I just said. To differentiate the y squared with respect to x, we're using the chain rule with the outer function being the square function, the inner function being y. And so the derivative of the inner function, remember that's part of the chain rule. We look at differentiating the inside or inner function. That's going to be dy dx derivative. So what's going to happen in practice? You're not going to think, I'm using the chain rule every time you do this. You're probably just going to, like we said, differentiate as usual and then just put that dy dx factor whenever you're differentiating something with y. And that's okay. That's what you do in practice. But remember, the reason that this works and what's going on here is the chain rule. That makes it work. Okay, so quick example here. And this one I am going to work out. So we want to find dy dx. So we're going to start by differentiating both sides of the equation. And for this first term here, I'm going to use the product rule because I've got a function times a function. So product rule tells me negative sine 3x times the derivative of the inside, which is 3. So I'm using the chain rule as part of that, times y squared plus cosine of 3x, this function, times the derivative of the second one, which would be 2y times dy dx, minus, I'm going to think of this as x plus y to the 1/2, 1/2 x plus y to the negative 1/2 times the derivative of the inside, which is 1 plus dy dx, plus 3y squared dy dx equals 0. So we've got all this is for this term, all this is for this term, and all this is for that guy. Okay, so now I got to get everything grouped together. I've got cosine 3x times 2y. I'm going to write it like this, 2y times cosine of 3x minus 1 over 2 times the square root of x plus y, this term, times the dy dx, plus 3y squared. Now, I'm a little bit cramped for space, so I'm kind of doing this a little bit quickly, but I'm keeping all the dy dx terms. There's one of them. Here, this times that is a second one, and this is a third. And then I'm going to add or subtract appropriately from both sides of the equation to get the non-dy dx terms on the other side of the equation. So 3y squared sine of 3x, add that to both sides, and then plus 1 over 2 times the square root of x plus y. All right, and so I've got like we said, we're always going to be able to do this. It might just look really terrible, and this is going to look really terrible. But dy dx is going to be now 3y squared times sine of 3x plus 1 over 2 times the square root of x plus y all over 2y times cosine of 3x minus 1 over 2 times the square root of x plus y plus 3y squared. And there's things we can do to make that maybe look a little nicer, but we got an answer. So super messy, not maybe a standard nice first example. Maybe you look at the circle for that, but just kind of illustrating a couple of tricky things along the way. We can use rules we know, product rule, so on, and it can get certainly a little bit messy there. Okay. The last thing I want to mention is something kind of a neat application of this. We previously talked about the trig functions, but we haven't looked at their inverses. So, sometimes folks will write or say arcsine instead of inverse sine. It's the same thing. You just want to know that this doesn't mean 1 over sine, because that would just be cosecant. So it's the notation for the inverse function. Just want to remember that. But we haven't talked about what those derivatives are. Those are perfectly reasonable functions, especially in applications. We want to know that. So to find these formulas, we can use implicit differentiation. And here's just one example, finding it for this function, inverse sine or arcsine. So you start out with just your function in question, and I'm going to write it, I'm going to think about it as if y equals inverse sine of x, I'm going to say sine of y equals x. That's what it means in terms of the inverse function description. And so now I can use implicit differentiation. So differentiating this side, I get cosine of y times the derivative of y with respect to x. The derivative of x with respect to x is just 1. And so I've got dy dx equals 1 over cosine of y. Well, I started off with y as an explicitly defined function of x, so maybe I want to try to do that with the derivative. So can I find this in terms of x? And we can. If we remember that for arcsine or for inverse sine, we have this restriction. Y is between negative pi over 2 and pi over 2. So that means that if you think about the graphs, you can justify this if you like, but that means that cosine of y over this interval cosine in general is not always positive, but over that interval cosine would be positive. And so when you use the Pythagorean property, so sine squared plus cosine squared equals 1, or this manipulation of it, solving for cosine, I would have potentially plus and minus roots, but since cosine is not negative, I just have the positive root over that interval. And so that description of cosine y, I can stick that back in down here, and that tells me the derivative of arcsine is 1 over the square root of 1 minus x squared. You do the same process with the other 6 inverse trig functions, and this is what you'll come up with. So this would probably be something where it's worthwhile just to memorize these. You don't want to have to derive them from scratch, but you can using implicit differentiation. It looks like there's 6 things to remember, but you'll see that a lot of these are kind of connected. Arctangent and arccotangent just differ by a factor of -1. Sine and cosine differ by a factor of -1. Secant, cosecant differ by a factor of -1. So it's kind of like you remember 3 things, and then with the cofunctions you tack on that negative. Maybe that's the way to do it. But it is a neat application of implicit differentiation, which is again an application of the chain rule.